Okay, so for this last lecture, we're going to mainly be discussing the Kitaev model, the Honeycomb Kitaev model. And so actually the Honeycomb lattice, you know, it has two inequivalent sites, so it has the A and the B sublattices. So for example, we can call this the A sublattice and this the B sublattice. But there are also three translationally inequivalent bonds, and we can write a label for these bonds, and we might as well call them type X, type Y, and type Z. And actually, the rationale for this comes from the fact that these materials can be, the honeycomb lattice can actually be embedded in a cubic structure. And in fact, the materials that, for example, the iridates, they're essentially, well, at least more or less embedded in a cubic structure. And actually, if you now, instead of taking your 2D plane, now you take your 2D plane to be embedded in this cubic lattice with the 1, 1, 1 axis here being the one which is out of the honeycomb plane, you can actually see that the X bonds here can be labeled in this plane here, which is perpendicular to the global X-axis, to the cubic X-axis, while the Z bond would be perpendicular to the cubic Z-axis, and the Y bond would be perpendicular it would be lying in the plane perpendicular to the cubic y-axis. Okay, but this is kind of to understand the labeling and to see how it fits in 3D when actually the materials, it's not just going to be one plane, but it's going to be a number of layers, more or less insulating layers, non-interacting layers of honeycomb lattices. Okay, so that's all for this. Yeah, if you can help me, that would be great. And so the Kitaev honeycomb model, and I'll try to remember to write big Kitaev honeycomb model. It was put on the archive in 2005. So it's a paper by Kitaev, and the reference is on archive 0506 438. But actually, the model was discussed, I think, for the first time publicly at the KITP in 2000. Okay. And it was basically the first an ambiguous model for a quantum spin liquid, and it's exactly soluble, so all of these questions of approximations, etc., won't be arising. Okay. So what's the model? So it's spin 1/2 on the sides of the honeycomb lattice, and the Hamiltonian. So the Kitaev part of the Hamiltonian takes this form. So it's a sum over nearest neighbors, Jx, Six, Sjx. And here, I'm only summing over ij belonging to x. So this is obviously an abuse of notation, but what I mean is that the only bonds I'm summing over for this term are the bonds which are X-type bonds, okay? So this guy only exists over this bond, this bond, this bond, and all the other X-type bonds, okay? But we also have terms for the other bonds. They just take a different form, and it's this one. And finally, the last ones exist only on the Z-type bonds. Okay. So it's not a Heisenberg model because the sum is not over all bonds for every term, and it's a completely anisotropic model, so if you were to realize it in an experiment, you'd actually need strong spin-orbit coupling. Actually, at the beginning, in 2005, Kitaev just wrote it down as a model. You know, you can always allowed to write this down, but later, Jackelli and Kaludin, as we'll see, actually showed that this really weird-looking Hamiltonian could actually be realized in real materials, which sparked a huge amount of interest. Okay, so Kitaev not only provided the model, but he also provided the solution for this model, so an exact solution. And so the way that he did this was actually through defining this, you know, having a rewriting for the spin operators, but here in terms of Majorana operators. And so mu here is x, y, or z. And so what Kitaev wrote down was that S mu would be SI mu would be I C mu I. And so there are actually 4 of these C fermion operators, one which doesn't have a label, and then which is common to all components of the spin, and then 3 which depend on the index, which only appear for the spins that have the same index. And there has to be a constraint here, which is that we must project the spin operators to be such that the states have to be projected. So there's a constraint, which is that di psi so this has to be true, where di is Cix, Cjx, Cix, Ciy, Ciz, Ci. Okay, so it's a little bit like we were saying that actually this thing had to be 1. This is kind of an abuse of notation. So this is the constraint here. So let me tell you what a Majorana fermion is, because maybe not all of you have seen this. So actually, a Majorana fermion is kind of hard to know what that is, but we know what Majorana fermion operators are. And they are operators such that, here I'll write it in general. So if eta is a Majorana fermion, it is such that eta dagger equals eta, okay? And in particular from here, you can actually see that then this operator is not going to be, so eta dagger eta is not going to be a number operator. So in fact, the number of Majorana fermions is not well defined, which is why a Majorana state itself is kind of difficult to understand. And it's a fermion, so that's the Majorana characteristic, and it's a fermion, so it has fermionic anti-commutation relations. And so we have that S for some Majorana operator eta I. We also have another Majorana operator eta J. We have that this is 2 because eta is 1, 2 delta ij. So that's just the fermion, the fermionic part, okay? There, again, you can't really define a state for these, but what you can do is actually once you take 2 Majorana fermion operators, then that defines an actual fermion. So they're kind of half of a fermion. So actually, if you have any real fermion operator, can actually be written as some Majorana operator C1 plus I C2, and we have that F dagger equals C1 minus I C2. And then we have the proper commutation relation for the fermion, so we have these are, this is good. Okay. And because they're so funny, actually, if you take the Fourier transform, a good definition for a Fourier transform of a Majorana operator is actually that eta I is 1 over n, sum over k, so only half of the k's. So, for example, we can take all the k's, but we'd want kx positive. That's a choice, which when you choose, it's just that there are kind of not enough degrees of freedom for Majorana operators to actually have this span all of the k's, and so this would be ck e to the I k dot ri plus ck dagger e to the I minus I k dot ri. And so with this, you can actually check that indeed you have eta I dagger equals eta I, was the definition. And these guys are actually regular fermions. But they only exist for half of the case. Okay. All right. So, okay. And so now what happens, so the reason that this helps us actually solve the Hamiltonian exactly is that if you actually plug this in, so we like to plug in things, our decompositions, we'll always like to plug them back into the Hamiltonian. And so for here, we actually see, so I'm going to rewrite the Hamiltonian in a shorter form. So I'm going to write this in mu, again with the same abuse of notation, and it's j mu si mu sj mu, okay? And so we can plug our equation here into the Hamiltonian, and so we get that we have a sum of mu, sum ij in mu, j mu. So there's a minus because of the two I factors, and now we have ci, ci mu, cj mu. Okay. And now I can have this fermion operator, and I can move it there, so then that takes the minus sign away, and so we have j mu, ci, cj, ci mu, cj mu. And so what you actually see here is that the magic of this reformulation is actually that each one of the c mu's, okay, appears only in one term, okay? So if you define this to be uij, just by, it's a definition here, okay, this operator uij, it doesn't need a mu here because ij implicitly defines what the mu should be. Then you actually can see that uij, ukl is 0. Okay. So you can do this explicitly. It's kind of simple. Basically, all of these, because they only appear in only one bond term, actually you only have bosons here that commute with one another, and there is no common term in either one of these. Okay, so this is 0. And so this tells us that all of these variables, since they all commute with one another, one can actually choose them independently to have a value, so they become, in this solution, kind of like classical variables, and we can get a sector for each one of we can have a sector for each one of the values of ui, and so uij can just be chosen to be plus or minus 1. So now if we actually rewrite this, all right, and we also have Uij, h equals 0. I guess that was also important for solving the Hamiltonian. Okay. So now we can just, and actually, I guess this takes an I. By the usual definition is to say, so this would be Uij divided by I. Otherwise, it would be plus or minus I, actually. And so the Hamiltonian now actually takes the form of h equals I over 4 sum. I mean, just not define this like this because it's going to be confusing. Just I, Uij, Ci, Cj. Okay. So now this actually looks like a quadratic Hamiltonian, where we can solve it for every value of Uij that we like. So now we basically solve it in every sector of Uij that we like. And what Kitaev tells us is that there cannot be vortices. Yes. Into vacuum. Here it is. Yeah, I think that should be fine. Well, that's what I was mentioning. You could write it, but actually Ij implicitly defines the index mu because the bond Ij sits on a bond mu, which is singly defined. So if you want an index, you can put it, but you don't have to. It's already defined in there. So what Kitaev tells us is there cannot be any vortices in the ground state. Okay. So where do vortices come from? So vortices actually are going to be, so this is going to be playing the role of a gauge field, and the product of the U's around the hexagon are going to be playing the role of a flux. And so if vortex, in other words, is a -1 flux. Okay. So, yes.
Why the restriction to kx bigger than 0?
So because these operators are Majorana fermion operators, and so you need actually 2 to make a fermion, okay? An actual fermion which really has, lives in the fermionic Fock space and really is a true fermion. And these guys are regular fermions. And so now if you're taking these guys to be regular fermions, which you should do, sorry, I should have said eta here, I'm sorry. Inconsistent. If you take these guys to be regular fermions, then you should have only half of the degrees of freedom. So the choice of saying I'm taking only kx positive could also be ky positive, or any choice that you might like, but this is kind of a convenient choice. But just keeping track, basically, of the appropriate number of states.
What happens if you double put all kx there?
Well, I guess what you have is then you have too many of these to define that one.
They will not be the same, will they?
You will just have over-defined things, so there is not going to be any corresponding one on the left side. Yeah? Yes?
Can you explain why there are no vortices in the ground state?
That's just kind of a so I think there's some proof by Lieb, which I don't know. But so I guess you know, for example, also in a fluid, that the ground state, there's no vortices, and just take a fluid, then there's no vortices in there. So these play the role of excitations, and actually we'll see that they have an energy above the ground state. So yeah, I don't know if I have a good answer for you. But what you could see, I mean, it's not the same. So, but all of, for example, in electromagnetism, we know that we have divergence of E and divergence of B are zero in the ground state. And so that's kind of the same constraint, but because these would, so particles, right, if you have a particle, right, then you'd have divergence of E equals Q. And that corresponds to a vortex. So another word for a vortex would be a charge. And we know, for example, in electromagnetism, that the ground state is such that divergence E and divergence B are zero. So this is the same kind of thing. Be no vortices in the ground state. So let me define actually what are these vortices. So what are the charges? Well, yes. Yes. In K-space. But I'm summing only over half of them. Well, so you have to, sorry? Oh, here it's just that I didn't want to, it's the same, eta is some generic, this is true for all Majorana fermions in the world, okay? And C are the fermions I'm defining here. This could also be just eta 1, eta 2, maybe that's what I should have done. I can explain the reason why I chose eta and not C is I didn't want to confuse you, because here if I wrote C, you might have asked me, why did you write C? Is it the same for the C mu's? So eta here for us could be Ci, or it could be Ci mu, or it could be any Majorana fermion. This is true for all Majorana fermions. Okay. All right, so yeah, I guess so. I guess the operator which creates them in the operator which creates them in Fourier space is you can count them, I guess. So this is a good operator. This is indeed a number operator. But in real space, you can't, because you have this. So it's not me defining all these things, right? So it's Kitaev and various other people before them. Actually, Majorana fermions came first from high energy physics, and you can see them, I guess, solving the Dirac equation for some conditions. You can find solutions to the Dirac equation in the form of Majorana fermions. So they're kind of, so at the start, they're mathematical objects that indeed you can write down. And then if you want everything to be consistent, then this is how you have to do it. Okay. So it's weird, but it works. And so it's, yeah. All right, so what is so what do I mean by vortex? So we kind of found our gauge field, which was this U. And so we now have our vortex, which would be our flux. So it would be, for the theory we saw before, it would correspond to curl of A. Okay, so that would be another word for vortex, or flux, or this is a gapped particle. Okay. And so our vortex actually is defined through the operator P, where P defines a plaquette, so I could also have written a hexagon. And so on every hexagon, it's going to be the sum. So if I take a hexagon here, and I define its side to be 1, 2, 3, 4, 5, 6, and I have Z, Y, X, etc., then the W of this plaquette here, of this hexagon, is going to be sigma 1 X, okay, because the X bond is the one that's not involved in this hexagon, sigma 2 Z, sigma 3 Y, sigma 4 X, sigma 5 Z, sigma 6 Y. Okay. And it turns out that this operator also, in this case, commutes with the Hamiltonian. But this is kind of very specific to this model, and this condition actually is not going to be true once we start adding more terms to this Hamiltonian. So this is kind of a little bit of a sick point in some sense. And actually, this W operator turns out to be also equal to, so if you rewrite everything down, plugging in this thing over there and the definition for U, it actually turns out to be this operator, Uij, with Ij belonging to the hexagon. So you'd have to sum, you'd have to do the product of Uij here, Uij there, etc. Understand the notation? Yeah? Okay. So this, in the ground state, actually, we're told that the W's, so W, all W's over all hexagons, have to be 1 in the ground state. And so one way, for example, to achieve this is just to choose that all the Uij's are 1. And we know that we're allowed to do this because although Uij's commute with one another, and of course with the Hamiltonian H. Okay? So one solution to that constraint, which tells us what the ground state should be, is to actually take for ground state Uij equals 1 for all ij. Okay. And so now if you plug this back into our Hamiltonian here, okay, you can actually now what you have, since you fixed the value of this is obviously fixed since it's a parameter of the model, then you actually end up with a quadratic Hamiltonian here. And quadratic Hamiltonians are basically the only thing that we know how to solve, and so indeed we can solve it. So the way to solve a model in a periodic lattice is actually to go to K-space, and so I showed you what the Fourier transform was for Majorana fermions. There were lots of questions about this, but by just plugging this in to the Hamiltonian, you actually get a 2x2 matrix because you have a two-site lattice, right? The Honeycomb lattice is a two-site lattice, and you end up with a matrix whose eigenvalues you can get, and then you solve H, and so you actually get that the dispersion relation of these Majorana fermions in K-space actually is equal to plus or minus 2. So this is an exercise that you can do. Should be very simple. e to the I k dot n1, I'll define what n1 and n2 are, plus jy e to the I k dot n2 plus jz, okay, where n1 and 2 are plus or minus square root of 3 over 2, 3 over 2. Okay. We're actually, this is defined for lattice, which we've rotated by 90 degrees, but okay. So what you can see actually from this dispersion relation is that you actually, when jx is less than jy plus jz, and jy is less than jx plus jz, and jz is less than jx plus jy, then what you actually get is that you have k points in reciprocal space. Okay, so this would be k space now, okay, and you actually have k points I define this to be, for example, no, you have k points here along this axis, which can be, the location of the Dirac points will depend on the values of jx, jy, jz. So they're going to be, well, probably actually, they're going to be inside. So you're going to be having Dirac points on the x-axis, and actually they're going to be located at the k points here when jx equals jy equals jz. So what you have is actually you have a gapless phase anytime that these constraints are satisfied. So then the system is gapless with gapless Majorana modes. Dirac cones. When these are not satisfied, so when when this equation is not satisfied, then these guys are actually gapped, okay? Then cones Dirac are gapped. And actually this is the same phase. So the phase, it's you get a gapped phase, which is the equal to the phase of the toric code, which I don't have time to discuss, but this is a Z2 gauge theory. And it is one of the simplest quantum spin liquid states. Okay. And so there is a famous phase diagram which summarizes these findings. Okay. Which is, so Kitaev in his paper drew it this way. And so this is jx, jy, jz, and here this is gapless. So gapless. It's this guy we were talking about with the 2 Majorana cones. And these are the gapped phases. It's the toric code. So that's a picture that Kitaev drew, and so it summarizes these findings that we have here. Okay. So what are the excitations? So we already saw some of the excitations, right? There's these Majorana modes. So basically, the ground state, so in the gapless phase, which is really the phase which is very interesting, the toric code you can get by other means. This gapless phase of Kitaev is usually the one that's called the Kitaev spin liquid. So the ground state is basically having Majorana fermions filling these 2 Dirac cones. Well, these Dirac cones at K and K. Okay. We don't have the Dirac cones at K prime because we only have half the degrees of freedom. Okay. And so the excitations, so there are the gapless excitations. There are the Majorana excitations, so there are the Majorana Dirac excitations. And then we also have gapped excitations in the same phase. We have both, which are the fluxes, and which are such that WP equals -1. Okay? And so they basically correspond. So if you have your honeycomb lattice here, they correspond to fluxes here such that WP, equals -1, and they can be moved around. And in fact, what you see is that since the WPs are the products of the Uij, so P is a plaquette, so it's a hexagon. P could be this little hexagon I drew before. You actually see that a plaquette here you can change by flipping this. So for example, 1 WP could be because you actually have a flipped bond here. Okay, so because you actually have a Uij, which would be -1 on this bond. Okay, but you could move this around, actually. If you actually flipped, if you now flipped the sign here, so here I'm assuming that everywhere else I have ones, okay, except maybe, okay. So if I flip this guy here, then I'm going to restore this one being +1 now, and now the bad plaquette will I move to here, and now the flux. I mean flipped in the sense of WP equals -1 instead of WP equals 1. And in order to move it, okay, so physically, in this Hamiltonian, because WP commutes with the whole Hamiltonian, there are no terms in the Hamiltonian that actually do this. So the plaquettes in this minimal model are actually fixed and they have no dispersion whatsoever. But if you add a term like the Heisenberg term, they can move around, because now you will have introduced dynamics for the plaquettes. However, a color code.
It's sort of beyond it's a code you can use in a quantum computer to stabilize it.
Well, when it's gapless, I don't think you can do that. But in the toric code, indeed, can be used for quantum computation, and that was also thanks to Kitaev that we know this kind of stuff. But so let me move on. So the dynamics in this minimal model don't have any dynamics. However, let me again make a connection with what I said before, that if you flip a spin, you actually, locally, you actually create several of these flux excitations. You look confused. Was it okay? So this is just a definition. I'm just telling you that the gapped excitations are plaquettes which are -1. Okay? Yes, because indeed, locally, you can only create several plaquettes at a time. However, I would have been able to separate these two plaquettes. So now I'm going to create a spin excitation. And actually, if I flip a spin, what I'm going to create is I'm going to create several plaquettes that are flipped. Okay? Okay. So I'm going to get this wrong. I'm sure I'm going to get this wrong. So let me imagine that, so in the ground state, I have all the uij's that are equal to 1, okay? And let me imagine that I'm able to flip uij to be -1. The reason I'm not doing it with spins is actually that the spins create all sorts of things, but you should realize that this should be possible to create a to create a uij equals -1 by, I guess, if you do uij, ujk, maybe you can get minus ci mu this is ci mu cj mu times cj mu ck ck nu cj ck nu, and so this is just, no, it's not 1 because it's not the same. Anyway, I can't do it right now, but you can make these guys, okay, by writing the right spin operators, okay? And so if you start flipping one uij, what you actually get is you get locally that you actually have two plaquettes which are wp equals -1. Okay? And now if you act here, again, if you flip this guy by acting with the appropriate product of spin operators, then, okay, then now this plaquette is fixed, it's back to 1, but now this one has acquired a WP equals -1, and you can keep moving it by flipping uij bonds.
Sorry, is there a combination of spin operators that gives the bond?
I'm sure there is, one way or another, there's a combination. it's local, so it's not going to be infinite. Okay, you can Uij. I'm sure you can build with some. I can't do it. I can't do it right now. Well, so I was being asked about.
Is there a combination of spin operators
That flip Uij. Yeah. There has to be, because it's just this. That's true. I was just trying to show that these things can move. But if the spin operator is here involved, if you just flip a spin, you create all sorts of things, because there's a Majorana fermion and there's this other guy. So what you can do, actually, one way to probably flip one, but you also create Majorana fermion excitation. In this case, is if you do Si mu, Sj nu, then you would actually get minus Ci, Ci mu, Cj, Cj nu. And so this would be Ci, Cj, Ci mu, Cj nu. So if you take Si mu here, you can actually see that you can flip this. Maybe it should be another one. Anyway, there is a simple way to flip a spin. You may also create Majorana fermions with it, but there is a way to create a Uij, which is -1, provided perhaps you create Majorana fermion excitations. You can just work this out. It's all just algebra. Okay, I'm sorry. All right, so these are the excitations, and as I mentioned, but it's specific to the Kitaev model. You'd have a spectrum in K-space and energy where you have gapless modes, and then you have gapped fluxes, okay, which are of the order of J mu. And they can't move within this model, but they're going to have some bandwidth here for them once we start adding extra terms, which give the fluxes some dynamics. Okay. All right, so this was actually Kitaev model, as I mentioned, was just proposed as a model, but then Jackelli and Kalyulin in 2009, I think, proposed that the Kitaev term, by which I mean this guy I wrote over there, was actually was dominant in materials which had with specific bonding angles. I'll describe this in a second, but I won't go through their derivation. All I want to say is that what they found was that if you actually, so these materials are 3D materials, and so the first thing they proposed was for this material, sodium iridate, I think, where the iridiums are the effective spin 1/2. Okay, on the honeycomb lattice, but then actually the exchange path, a little bit like Giovanni showed you. I mean, he didn't do it in detail, but there is some oxygen octahedra, so there are oxygens around these iridium atoms. And now I have to draw it in 3D, but I think Radu will probably show the structure of this. Okay, and it turns out that the oxygens approximately form here. So there are in particular 2 oxygens, so one sitting here and another one sitting there. And here there are 90-degree bonds, okay? And the electrons, which are here in d orbitals, okay? And then you have oxygens, which are in their p orbitals, okay? They actually, the overlap, which leads to these exchange constants, actually is such that the hexagon, actually I'm getting it wrong. Yeah, so the Heisenberg, so the Kitaev term comes from these 90-degree bonds, and then you'd have extra terms actually, which come, so for the example, the Heisenberg term, which would come from the fact that you could have direct exchange between these sides. Right. What Jackelli and Kalulin showed was that when you have this geometry, the Heisenberg term is, if it's exactly 90 degrees, I guess, then you actually get a 0 contribution. So, because in principle, the Hamiltonian that you can write is actually only constrained by symmetries, and then you can do microscopics to ask what the largest values should be, okay? But the general Hamiltonian you can write on the Honeycomb lattice actually has 3 terms, okay? It has the H Kitaev, and so Jackelli and Kalulin's work was to show this could exist and large for such materials. Then you have a Heisenberg contribution, which is just Si dot Sj on every bond. Maybe we put a J here. And then you have a so-called gamma term, which is some symmetric term, which has some form like this, gamma, sum over ij bonds, si mu, sj nu plus si nu, sj mu. Well, I guess they don't belong to mu or nu. Okay? And so this is the general Hamiltonian for a honeycomb lattice with strong spin-orbit coupling. And what Kitaev, Jackelli, and Kalulin showed was this actually would be the dominant term in such compounds. And so here there's no, it's difficult to, so they wanted to try and see what the effect of these other terms would be on the model, if you, how far the Kitaev spin liquid would be stable. So what you have to realize is if you actually have a material which has only this term, you know for sure that you're in one of these quantum spin liquid phases. If you add these terms in perturbation theory, you know that you have to be stable because the quantum spin liquid is stable, but these become large, then actually you're in trouble because then you get ordered phases. And Jackelli, Chalupka, and Kalulin actually showed that for this would be for the Kitaev Heisenberg model only, so not this guy. And they did ED, exact diagonalization, and they showed that the Kitaev phase, Kitaev gapless, was stable here, and it was stable here. They also take, so this would be true in these materials, where you have Jx equals Jy equals Jz. because of threefold symmetry. So that would be the Kitaev gapless also. And everywhere else in the phase diagram, yeah, I'm going to say this in a second. These are all various ordered phases. And so what this circle is every point here on the circle, so every point in the phase diagram corresponds to an angle phi. And the definition of this phi angle corresponds to the definition of the Kitaev and Heisenberg contributions, and they've defined them as follows. So here they write that their model here is 2k si sj mu plus j si dot sj. So k here is our jx equals jy equals jz. And what they write is that k equals a, well, basically is proportional to sine phi, and j is proportional to cosine phi. Okay, so basically sitting on this phase diagram that tells you what the relative strength of k and j is. Okay, and so the Kitaev is stable only in pretty small regions of the phase diagram. Yes. 24 side cluster, apparently. Well, here there are no parameters, so here they're just trying to map out the phase diagram for all possible phis, meaning for all possible phase diagrams. So this compound just has the right kind of bond angles such that the Kitaev terms would be large compared to the Heisenberg term. Okay, but now we don't know exactly what the values of the relative strength is for this material. So they just wanted to map out where this would be stable. And actually, it turns out that sodium iridate, also ruthenium trichloride, they actually are in an ordered phase. Okay, so we know they're not here. And Radu will tell you about this, I guess. What there has been now is there's been some estimates for these values. I don't know them by heart. There's been some estimates from some ab initio calculations and from experiments. But I don't have them in my mind. There are tons and tons and tons of different proposals for these.
Which one is the bigger range, the ferromagnetic one or the
I guess the ferromagnetic one.
The lower one is the ferromagnetic?
Yeah, I think so. It's all in their paper. Okay. So that's actually very, very nice. There are lots of material. Well, I don't know about lots, but there are various materials that you can make that have this structure. And in particular, one of the more recent compounds. So the first all started with these iridates, but then I don't know how long ago now, maybe 5 years ago. People starting to look at another compound, which was ruthenium trichloride. And here it's 4D, and it's also effective spin was 1/2. This is a 5D ion transition metal. This is also ordered. Okay, so it's also not a Kitaev liquid. In fact, it's ordered in a zigzag phase. But what happens, and this seems to be actually very interesting, is what happens when you apply a magnetic field to these materials. And actually, Kitaev told us why it's interesting to apply a magnetic field. So, in fact, so if you take the general Hamiltonian here, H, this would be H in zero field. This is H in zero field, but you can also add to this a magnetic field because you're allowed to apply a magnetic field to your system. And so in this case, you actually would have a magnetic field H here, and then it couples to the spins SI. Okay. And there can be some G factors, I guess, so more precisely, it would be something like this. So matrix Z, which is the Z tensor. Okay. And it tells you how much, this tells you about single ion anisotropy. Okay. And there's no exact solution when you apply a magnetic field. However, you can do perturbation theory. So if you do perturbation theory, keeping, for simplicity's sake, just this guy and this guy, so perturbation theory in H over J mu, okay? So pure Kitaev model, meaning none of the Heisenberg term or gamma terms. Again, you can do the derivation, but it's long. But there's an argument which shows you that you actually expect what you expect. You accept the Majoranas to become gapped as a function of h cubed. And this is the reason. So one way to do perturbation theory, which is in my view the simplest way, is to do Brillouin-Wigner perturbation theory. And the way that this goes is actually that you get a H effective. This is also how you can derive the H effective from quantum spin ice using Brillouin-Wigner perturbation theory. And it tells you that H effective is the projection onto the ground state times the interaction here. So for us, it would be the H field in our case. And then some, basically it's 1 minus P over the energy of the state you're looking at minus the energy of the ground state, and then times V times 1 minus P times V again times P in the ground states. This is all ground state. Okay. So this would be a third order because you can check that the other orders don't contribute to creating a gap. In a third order, however, you open a gap in the Majorana fermion. So at third order Majoranas get gapped. And because you know it's at third order, and you know that this is coming from that at third order you should get an effective Hamiltonian which takes this form, then you actually know that the scale of the gap
First order, of course, you'll always get out of the space.
yes. I don't remember. Yes. Sure. Yeah. No, probably even more, no? Not 3? Yeah. I guess because there is a... Yeah, yeah. 2 flux, yes, okay. Yeah. Good. Okay. Yeah.
It's all on the same sites basically.
Yeah, just a second. Okay. Okay. So if you act, so you have a term which is that's okay. So if you act with a field once, then you would flip. So if this is x and you act with sx, so you act with hx is x, then you create flux here, and also some Majoranas. So then you want to act, maybe it's here actually, probably here. Let me do it. You have to cancel this plaquette. That one. So then you do this one. Yeah. Okay, so here, if it's a y, this would be x. So then you do, here you would do h, y, s, y. So now you have one here and one there. And now you act here. With, so this would be a z bond. So here you act with h, z, s, z. And so you've canceled this already from acting with sy here. Now you cancel this guy again, and now you cancel all fluxes. Because the point is always, because you're projecting back to the ground state, so it means that you can't have any fluxes left, okay? This clear for everybody? It's not so difficult. And then on the way, you've also created some Majorana excitations because you have these guys acting on it. Okay? So by acting 3 times, you actually manage to get back to the ground state. If you acted only twice, you could have acted again on this site to cancel those 2 fluxes again, but this would just be a constant. Okay, so you have to go 3 times to get back to the 0 hexagon configuration. Yes? It's the projection onto the ground state, because when you do perturbation theory and you're asking what the perturbation does to the ground state or ground state manifold, then you always have to project back to the ground state. That's what perturbation theory does. Okay? All right, so what we see actually from this formula is that our perturbation here is H field, so this goes, as H, and actually we saw that it should be all 3 different terms here. It should be one Hx, one Hy, and one Hc. So here, for example, here we have Hx, Hy, and Hz. And then over here, the excitations that we've created are actually the energy of a, flipped plaquettes is actually of order the Kitaev term. Okay, so this is of order J, or K, or JK, J Kitaev, which is JX, JY, JZ. So what you actually see is that you have now a perturbative state, okay, which has a gap, which should be of order delta, which is XX, HY, HZ over J squared. Okay. So what happens is that now you add your Dirac cones here of Majoranas, and now they become gapped within perturbation theory here, with a gap here that's of order delta. And in fact, I think there's the exact expression, which is this. So epsilon q here, where epsilon of q is plus or minus 3j squared delta q squared plus delta, so I should just write, if I write q star to be the location of my Dirac point, then you have this q star minus q squared plus delta squared. So this is the dispersion that you can find if you do the calculation exactly.
Just to clarify,
Yeah.
this is J denominator. This is J.
This is this guy. So here, yeah, J Kitaev. So in this little calculation, but this should not, it just would be more complicated, but wouldn't change the physics. You could also add the Heisenberg operators, so long as you're staying in the gapless phase, so it would have to be a tiny little Heisenberg term. Would still get the same kind of thing, but here the calculation is carried out only for pure Kitaev model in the gapless phase.
A magnetic field applied in a direction that has one of the three terms 0 at x, y, or z.
Yeah, then it doesn't create a gap. You need all three, and another point actually is that this is in the coordinates of the cubic lattice. So these are actually the coordinates of the, these are the cubic coordinates. Okay. However, the fact that it's cubic is only because we're looking at a finely tuned point in the phase diagram. So we're looking at the pure Kitaev model, and actually the general scaling of the gap, is of order h. If you add Heisenberg terms as well, and this was, it's not the specific form, but this was also done in a paper by Leon in 2016 probably. Okay. So basically, if you look at your, if now I'm asking about, this is, hx, hy, hz. There are planes here for the pure Kitaev model where the gap vanishes. So if you apply a field in some directions, you don't open a gap and you stay in the phase diagram. And actually for for the Heisenberg model, or for the Kitaev-Heisenberg model, it's only going to be some surface here where the field vanishes. Might be some complicated surface because it's not just a pure direction, it's just a linear function of h. Okay. So what's this phase? So it's a gapped phase. It's interesting, but it's much more interesting than the toric code, actually, because it's a special phase which actually has Majorana edge modes. So it's gapless in the bulk. It's gapped in the bulk, but it's gapless at the surface. So basically, if you took, a chunk of your Kitaev plus field, what you actually have is here you have non-abelian, which means if you, let me finish, non-abelian vortices, so non-abelian fluxes, so it's the fluxes that we saw before, to which plus some Majoranas is bound to them. But they're gapped. And around the edge of the sample, in a direction which depends on the magnetic field, you have gapless edge modes.
What do you mean by non-abelian vortices?
Yes. So non-abelian means that you have statistics, right? And you know that for fermions, if you move one particle around another, you actually acquire phase pi, minus one phase, pi, so you acquire phase pi, so acquire minus one, so the wave function goes from psi to minus psi. And for bosons, it would just be, doesn't matter, okay, that you've rotated one and one the other. And for non-abelian particles are such that if you move one around another, it depends how you do it. So phase, so non-abelian, they're called anyons. And in fact, it's not necessarily just a plus or minus one phase. It depends on which order you do things in. Okay. But here, what we'll be more interested in, because these are all gapped, so the low energy theory doesn't actually probe these things. It can be useful, again, for quantum computation, because they're gapped and they're non-abelian. But what's of interest to us right now is this gapless mode, which can actually be described by a Hamiltonian around the edge. So Hamiltonian at the edge is the sum over x on the edge. Some factors. And it scales linearly. so I could just write it in k-space directly, actually. So the Hamiltonian around the edge is actually sum over q positive epsilon of q eta minus q eta q. And so out of this, you actually get a current, which you can calculate to be the number here, q, the energy of q, that's just the definition of the current along the edge, times the velocity, dq over 2 pi. So this is the fermion number, fermion Fermi function. This is the dispersion of edge Majoranas. And this is their velocity, which is just equal to d epsilon over dq. Okay, and so if you actually carry out this calculation, it's extremely simple. You actually get a current which is equal to pi c, which is the central charge. Saying just dropping lots of names here, but just no time over 12. So what you know is now that you have a current propagating along the edge, which is this big, and this is equal to 1/2 in this case. So it's fractional when you have phases which have non-abelian anyons. And so what happens actually, this has some consequences. If you now take a Hall bar, okay, so this is my system. Oh, sorry. Well, there is no charge current here because there's no charges, so it's the heat current along the edge. Okay? So if you take a Hall bar, then you're going to have some slightly hotter edge. So you apply some, so this would be hot and this would be cold. Well, actually, you are in a Hall bar geometry. And so here you have the temperature for the bottom phonons, which is slightly less than that for the top phonons. And so you actually get, and they're propagating in opposite directions because they're at the bottom of the Hall bar. You actually get a current which, for a small difference between the two, is actually approximately equal to c pi kb squared t over 6h times delta ty, where this is delta ty. And so since you're actually applying, you know, you have a current Hx, we know that the current Hx by definition should be the Hall current times the temperature difference in the y direction. That's just Fourier's law. Remember, Fourier's law is just that the current is minus the thermal conductivity kappa times the thermal gradient. So this you can identify with the Hall current, and what you actually get is that you have a half quantized thermal conductivity, which is pi Ct over 6. Okay, where T is the mean of T top and T bottom. And so you actually get a half, because C is half integer, so you get a half quantized Hall thermal conductivity, which is a smoking gun signature of this phase. And this was actually measured in Matsuda's experiment. Of course, it needs to be reproduced. But this is one way, and perhaps one of the only ways, that you could actually tell that a quantum spin liquid exists without any kind of ambiguity. That was very fast, but lots of this can be found in Kitaev papers and others. I guess I wanted to say a few conclusion words, but
You stood up just 3 minutes. Just standing up to make.
to give me some pressure. I had a page with lots of references for you. I don't really know. I guess I should just give you that as it. So I had lots of references for lattice gauge theory, but it's maybe more efficient if I just give them to you on the notes. Yeah, I'm gonna try. Yeah, well, I don't know. I mean, there are lots of things I didn't talk about. Maybe I should just make a list of this. But at least you'll have seen the words once, and maybe you could look them up. Okay. So there is resonating valence bond, which was what actually Colin showed you yesterday. This was the first example of a spin liquid. It's due to Anderson. There's the toric code. This is kind of basics you should know for quantum spin liquids. There's other parton constructions, which we didn't discuss, which are actually more common than the ones I just mentioned, but less physical. There's lots to do, and so that has to do with like PSG, projective symmetry group, and Guts filler. These are other things you might encounter. Guts filler, projection. There is various symmetry enrichments, which allows you to classify things. We actually talked about a little bit of this. There's the K-matrix formalism. And finally, it's actually more important than the last 2, 3. They're actually, I talked about entanglement by waving my hands more or less, but you can ask, can you calculate this in numerics or can you measure it? So for this, you can't wave your hands, you actually need a number or something. So there are various measures that gives you number of entanglement. So for example, entanglement entropy. And that has to do definitions, also related to the Schmidt decomposition. And that's very useful, for example, for tensor network states, etc., for DMRG. All right, thanks. So the magnetic field is what gives you the fact that you have the state. So you should think about it just like the quantum Hall effect, except here is for a thermal Hall effect.
So that current is for the sake of the thermal gradient, or it's for the sake of the magnetic field that you're applying?
What do you mean for the sake of?
I mean, what causes that they start going around there? That current is heat current. So
Yes.
the source of the current is thermally, or is because of the magnetic field?
Well, it's thermal current, but you need a magnetic field for it to exist.
Okay. So so they should be both together, right?
Yes, I mean,
And then second, so it means that magnetic field perpendicular and parallel to sample would both affect our sample, right?
well, so there were these questions about the fact of whether or not you could have a magnetic field in some directions that did not, you had this gap, so you can get into this phase by applying a magnetic field. But for some directions of the magnetic field, which for the pure Kitaev model are the anytime you have hx or hy or hz equals 0. For a more general model in some directions, which might be a complicated linear function of the magnetic field, then you cannot get into this phase, and so you would not be able to obtain this quantized value. In general, you can apply a field in some direction, any direction, but for some of them, you're going to get a 0 result.
And then it means that in that system, the temperature gradients would be something like that. That, for example, when we go to right, down, it's cold there, and when we come to left, up, it's
So actually, the temperature, isotemperature lines, like just like in quantum Hall, they're like this, okay? Except in the experiment, you actually, have a heat bath here, okay? And so that also creates the propagation of phonons, and so then the field lines, actually, in fact, they're almost perpendicular. But that's just because of the phonon. Maybe I shouldn't get into this. But if you don't have any phonons, the lines are just this way. The isotemperature lines are this way. Just for like Hall effect. In practice, in a real experiment, because of the phonons, and the phonons carry much more heat, then it's the other way. But for this model, it's this way.
sorry, just last question.
Yeah.
So would we also see thermal voltage there? I mean, in Majorana, do they have also some charge?
No. Purely heat. No charge. No charge and no electric charge anymore.
You have to be in the gapless phase in order for the magnetic field to create these Majorana modes?
Yes. In toric code, I mean, it's already gapped anyway. You don't actually really have Majorana modes there. At least if deep in the phase, you don't have Majorana modes at all. I mean, it's not a good description to use that. So the gapless Majorana modes come from applying a time reversal breaking perturbation on the gapless phase.